Assalamu alaikum. I hope everyone is well. So today we will start the new method of solving the nonlinear equation that is known as Newton-Raphson method. So this is another method of solving the nonlinear equations since it is a nonlinear equation, and this is again an iterative method. It has got various advantages over the GS method, and because of these advantages it is usually used in practice instead of Gauss-Seidel method. Let us try first, instead of going directly to use it for the load flow problem, we'll first try to do it for a one variable nonlinear equation, then another, then second variable, two variable nonlinear equation, and by doing that it will be slightly easier to understand when we go for using this for the load flow problem. Here we'll use it for a one variable nonlinear equation. Let us say we have a nonlinear equation fx is equal to 0. Here equation is fx and the variable is x. So as we know, as I have told you before, that the number of variables should be equal to the number of equations. Here equation is fx and variable is x. Let x naught be the initial guess, so that we'll put this in this fx instead of x, so that we can get some value. But it may not be the exact solution, because when we put some solution or initial guess to this, it may not be the exact solution, which might not result in fx is equal to 0. For example, if we have this equation x square minus 2x plus 1, and fx will be x square minus 2x plus 1, that is equal to 0. Let us say the initial guess will first put a value of x naught is equal to 0.5. When this is equal to 0.5, this equation comes out to be equal to 0.25. So this is actually 0.5, f 0.5, it is not 1.5. So which is not equal to 0, but it is initial guess. So we know that the solution for this equation is x is equal to 1. Therefore, correction delta x, that is the difference between the actual x, that is x naught, and the actual this solution will be 0.5. When we add this 0.5 to this, that means f of 0.5 plus 0.5, that is f of 1, that will be equal to 0. Or we can say f of x naught plus delta x, that will be equal to 0. So let x minus delta x is the correction to be made, so that x is equal to x naught plus delta x, which is the exact solution of the equation first, that is f of x. So like this, when we put f of x is equal to this x naught plus delta x, which is exactly equal to x, so it comes out to be f of 1, it will be equal to 0. Here also, let us say delta x is the correction, which is actually a deviation of the actual solution to the initial solution. So when we put this delta x into this, you will get, that's again f of x. Here we'll solve it in terms of x naught and delta x. So this comes out to be equal to 0. So expanding the equation 2 by Taylor series, we get f of x naught plus delta x will be equal to f of x naught plus df by dx solved at x is equal to x naught into delta x plus del square f by del x square. This also solved at x is equal to x naught into del x square plus del cube f by del x square. X is equal to x naught, that means this has to be solved for x is equal to x naught into delta x cube plus the higher order derivatives. We'll neglect the higher order derivatives because you will see for Newton-Raphson method to converge, this delta x should be very small, or we can say the initial guess should be close to the exact value. So delta x will be very small. So delta x square and delta x cube, they will be further small. So these higher order derivatives can be neglected. So I can write this as f of x naught plus delta x will be equal to f of x naught plus d by dx solved at x is equal to x naught into delta x. This will be equal to 0. I have forgot here to write it right. This should be equal to 0. So this delta x, when we solve the delta x from this equation, this delta x comes out to be equal to, I will take this to this side, to be minus f of x naught divided by df by dx, solved at x is equal to x naught. This is the value of the delta x naught, delta x. Or in general, this delta x is equal to minus f of x naught divided by f dash of x naught. Then x will be, actual x will be equal to x naught plus delta x, or x naught minus f of x naught divided by f dash of x naught. For any iteration or in general case, this xr plus 1 will be equal to xr plus delta x, which we have written over here. You can see this x plus x naught. We can say this can be equal to x delta x naught. This will be 1. That means this is the first iteration. So I can write it in terms of general iteration. Xr plus 1 is equal to xr plus delta x, or xr plus 1 is equal to xr minus f of xr f dash of xr. These are the in terms of different iterations. If r is equal to 0, this is equal to x1 r0 minus f of this xr f dash of f of x0 f dash of x0. So let us try to do one numerical. This is the same equation. Let us say we have one equation like this, the same equation which we have done for the Gauss-Seidel method. We have f of x plus cos x minus 3 is equal to 0. That means f of x is equal to x plus cos x minus 3. So f dash of x is equal to 1 minus sine of x. So delta x will be equal to minus f of x, that is the same value, divided by f dash of x, that we have written. Now here for the first iteration, when r is equal to 0, since we have started there also, x is equal to 1, this is xr plus 1. When x is equal to 1, xr plus 1, solving this delta x can be calculated like this, and xr plus 1 will be equal to this, because delta x will be equal to, x naught is equal to 1. So xr plus 1 is equal to this plus this. So this will be the xr plus 1 will be equal to this plus this. Similarly, for when the guess, or we can say down the value of the x will be equal to 2.0179, we'll put that in this equation. We'll get the value of delta x to be minus 0.018, and then xr plus 1 is equal to 1.9999. Similarly, when we put x is equal to this, we get this value. When we put x is equal to this, we get this value. So here you can see delta x has reached close to 0. It's a very small value, but I have calculated it to be equal to 0. You can see that this is slightly faster as compared to the Gauss-Seidel method. It is converging in less iterations. Here only 3 iterations, the solution has almost converged. Let us try to have one more, that is x square plus 2x plus 1 is equal to 0. F of x is equal to x square plus 2x is equal to 1. F dash of x is equal to 2x plus 2. So xr plus 1 is equal to xr minus, that is delta x, plus delta x, that's equal minus xr square plus twice xr plus 1 divided by 2x plus 2, that is f dash of x. Its value is also given over here. You can see I have started from minus 0.5 because I know that its solution is minus 1. So slightly closer to this. So this is xr, this will be xr plus 1, this is delta x. This is again when we put x is equal to minus 0.75, delta x will be equal to minus 0.125, and xr plus 1 is equal to minus 0.875. Similarly, when we put x is equal to minus 0.875, delta x will be equal to minus 0.075625, and xr plus 1, that is the updated value, will be this. Similarly, for the other iteration, you can see for this iteration it has come down to a very small value. In this case, this will converge. This is the Newton-Raphson method for a single variable nonlinear equation. Let us try to do this for a nonlinear equation where we have two variables, and for two variables we should have two equations. So we have two variables, so we should have two equations as well. Let us say these equations will be f1 xy is equal to 0 and f2 xy is equal to 0. Let x naught and y naught be the initial guess, and delta x naught and delta y naught be the correction to be made, so that x is equal to x naught plus delta x naught and y is equal to y naught plus delta y naught be the exact solution of this equation. So this is the same step which we have done earlier. So let x naught and y naught be the initial guess, and delta x, this is the same one. So f of f1 x naught plus delta x naught comma y naught plus delta y naught is equal to 0. Similarly, f2 x naught plus delta x naught comma y naught plus delta y naught will be equal to 0, because here are two variables and we are putting the two variables in this manner, so that putting the initial guess plus the correction will be the exact solution. So this is like this. So expanding the equation 2 by Taylor series, we get f1 will first expand this and then this. So f1 x naught y naught plus del f1 by del x. This is also solved at x is equal to x naught and y is equal to y naught, because this function will also be maybe the function of x naught and y naught into delta x naught, because this is differentiated with respect to x. Now we'll differentiate with respect to y. There is delta f1 by delta y. Again, this has to be solved at x is equal to x naught and y is equal to y naught into delta y naught plus higher order derivative. As I have told you that this delta y naught and delta x naught will be very small, and their square and their higher order power will be very small, and that can be neglected. Similarly, for f2, it will be equal to f2 x naught y naught plus del f2 by del x into del x naught. This is calculated x is equal to x naught and y is equal to y naught plus del f2 by del y into del y naught plus higher order derivative is equal to 0. So neglecting the higher order derivative and writing the equation 3 and 4 in terms of matrix form, we get, we'll try to form a matrix in which one matrix contains this function, another matrix contains derivatives, and then multiplied by these delta x and delta y. It can be shown like this. This is f1 x naught y naught, f2 x naught y naught plus, this will be actually f1 x naught y naught plus del f1 by del x delta x naught plus del f1 by del y delta y naught, and this whole is calculated x is equal to x naught, y is equal to y naught whole derivative. So this can be represented by this in terms of matrix form. So since we are here to find out the delta x and delta x naught and delta y naught, I will write down first this and take this to this side. It will be equal to delta f1 by delta x, this matrix multiplied with this matrix is equal to minus times of this matrix. So this can be written like this. Then delta x naught by delta y naught will be equal to minus, we'll take this to this side, it will be inverse of, when we actually pre-multiply both sides with this matrix into the inverse of this matrix will be the identity matrix, and here it will be multiplied as inverse of this. So delta x naught delta y naught will be equal to minus times del f1 by del x del f1 by del y del f2 by del x del f2 by del y inverse into f1 x naught y naught f2 x naught y naught. We can write it as like this. Delta x naught is equal to minus j inverse into f1, where j inverse is this matrix. This matrix is known as Jacobian matrix. It contains the derivative matrix. So this is the this deviation which we have, or we can say correction of the actual value of the solution and the initial guess, or whatever be the case it is. So minus j inverse f naught, and this, the order of these matrices is important. You can see here order is 2 is to 1, here order is 2 is to 2, 2 cross 2, and order for this, the initial value of the function is 2 is to 1. So for any iteration I can write it as this: delta x r is equal to minus j r f, this should have been f naught r. So x r plus 1 is equal to xr plus delta xr, or xr plus 1 is equal to xr minus jr inverse into fr. This should have not been, we should have written it as f naught. So I hope this you can do it on your own. So here it should not be f naught means the initial value, but here we are calculating only the first iteration. Since this fr has calculated here, it means if we are calculating this for 10th iteration, it should be f9. That means this function has to be calculated at x is equal to x9. So this is correct. This is not f naught. F naught is only here. Okay. Now let us try to do one more example for this case. So let us say x square is equal to 13 minus 5 square. It is a nonlinear equation in two variables, and xy is equal to 6. This is also a nonlinear equation in two variables. So I can make it in terms of f of x and y is equal to 0. That means I will take these to this side, and this will be equal to 0 equation. So this will be x square plus y square minus 13 is equal to 0, and this will be xy minus 6 is equal to 0. That means f1 xy will be equal to x square plus y square minus 13, and f2 xy is equal to xy minus 6. So let x naught be equal to 2 and y naught be equal to 1. Then f1 x naught y naught will be equal to, that means this will be 2 to the 4, 2 square, that's 4, plus 1 is 5, minus 13, that will be equal to minus 8. f2 xy will be equal to, that is 2 into 1 is 1, minus 6 is minus 4. So del f1 by del x will be equal to 2x, del f1 by del y will be equal to 2y. You can see it when we put the value of x naught is equal to 2, 2 to the 4, and x is equal to 1, this will be equal to 2. Similarly, del f2 by del x is equal to del f2 by del x is equal to y, and del f2 by del y is equal to x. Here we have to use the partial derivatives. So when you put the initial value is y naught 1, here it is 1, it will be 1. When you put the initial value, it will be 2. So all the calculations are done. Now we have to calculate delta x. So this is del f1 by del x, that is 2. Del f1 by del x should be equal to 4. Sorry, here it is 4. So del f1 by del y is 2. So del f1 by del x, del f2 by del x is 1. Del f2 by del y is 2. So it is correct, and this is the value of this. This is minus 4, 8. This is minus 4. So taking the inverse of this, this is 2, 4, minus 2, 1. This is 4, 4 to the 8, minus 2, minus 2. So I have multiplied this minus to this minus. So it will be plus 8 plus 4. It will be 1 by 6. So this is 2 4 the 2 at the 16 plus 16. Sorry, minus 2 to the 16 minus 8 is 8. This is minus 8 plus 16, this is again 8. So delta x naught is 8 by 6, and delta y naught is 8 by 6. So x1 will be equal to x naught plus delta x naught, that is 2 plus 8 by 6, and this is 1 plus 8 by, so this is the second value. This is the first iteration value of the x1 and y1. Similarly, we can calculate it for second iteration, delta f1 x1, that is when we put x is equal to, when we put x is equal to 20 by 6 and y is equal to 14 by 6, we'll get f1 x1 is equal to 32 by 9. Similarly, f2 xy is equal to 16 by 9. Delta f x1 is 40 by 6. Delta f1 by xy is equal to 20 by 6, 28 by 6. Similarly, delta f2 by delta x and delta f2 by delta y, that comes out to be these values. When we put all these values, we get delta x1 and delta x2 is equal to 16 by 51, and delta x2, this should have been delta y2 should have been 16 by 15. So x2 will be equal to x plus delta x1, that is 20 by 6 plus 16 by 15, it is equal to 3.64. So y2 is equal to y1 plus delta y1, 14 by 6 plus 16 by 51, it comes out to be equal to 45 by 70, that is 2.74. You can see it comes out to very close to 3. It is the actual value. It's 2.74, actual value is 2. When we go for 2 or 3 iteration, it will definitely converge. This is how when we do it for the two variable nonlinear equations. So let us try to do it for n variable n nonlinear equations. So let us say we have n variables, and n variables are x1, x2 up to xn, and we have n equations. The first one is f1 which is a function of all the variables x1, x2 up to n. We have f2, which is again the function of all the n variables to x2 up to dash 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 of, let us say we have fn nth equation, that is fn, that is, and which is also uh, dependent on all the variables, that is x1, x2 up to xn is equal to 0. So these are different equations. We'll do the same procedure, that will assume some initial guess x1 naught, x2 dot, xn naught, and we'll assume some corrections x1 delta x1 naught, delta x2 naught, delta xn naught. These are the correction to be made, so that these functions are equal to 0. That means f1 x1 dot plus delta x1 dot comma x2 dot plus x2 dot, x2 dot plus delta x2 dot plus xn plus delta xn naught will be equal to 0, so that this is the actual value. So these functions will be written now like this. In step 2, now we have n equations. So in general, all the equations can be written in one equation, that is fi x1 dot plus delta x dot x2 dot plus delta x2 dot dash up to xn dot plus delta x naught is equal to 0, where I is equal to 1, 2 dash up to n. So these all equations, n equations, can be written in one equations in terms of I, and then I can be varied from 1 to n. Expanding the equation by Taylor series and neglect the higher order terms. This, let us say, first we'll expand this equation in terms of Taylor series. It will be f1 x1 dot x2 dot dash up to xn dot delta f1 by x1 at calculated as x naught. This x naught is actually a vector calculating all the variable initial values into delta x1 naught plus delta f1 by delta x2. So here we have to differentiate it, the function, this first function, by all the variables, like we have differentiated. You can see it over here, like we have differentiated this function f1 first with respect to x, then with respect to y. So this is an n variable equation. We have to differentiate this first with the first variable, then the other variable up to the nth variable. So we have, you will see, we will have n terms over here apart from this. So it can be expanded. That means f1 can be expanded like this, delta this f1, this x1 naught, x2 dot, x2 naught dash up to xn naught plus delta f1 by x1. X is calculated x naught, delta x1 plus delta f1 by x2. Again, this is calculated x naught, delta x2 naught plus dash up to delta f1 by xn. Calculated x is equal to x and delta x1 is equal to 0. You can see I have defined this x naught is equal to the vector x1 naught, x2 naught dash up to xn naught. Here, this function is derivated at every variable. So we can find the derivative at every variable and multiply the correction of that variable, then we'll get this equal to 0. And here also we have neglected the higher order terms, in which we will get the second derivative, third derivative multiplied by delta x1 square root and delta x1 cube. Those we have neglected. So similarly, f2 can be calculated like this, f3, f4 dash up to fn can be calculated like this. So all these equations can be formed in one equation like this. Fi is equal to x1 naught, x2 dot, x2 naught dash up to xn naught plus del fi by del x1, calculated x is equal to x naught del x1 plus delta fi by delta x2, calculated x is equal to x naught delta x2 plus dash up to this delta fi by delta xn. Again, calculate x is equal to x naught, delta xn is equal to 0. When we vary the I, we'll get all the equations. I varies from 1 to n. So, writing these equations in terms of the matrix form, we will get, that is f1 x1 naught, can write as f1 f2 dash up to fn plus. So these two are to be taken into matrix form, that is delta f1 by delta x1, delta f1 by delta x2 should have in there, that is up to delta f1 by delta x. Similarly, delta f2 by delta x1, delta f2 by delta x2, delta f2 by delta xn. So this can be done up to I is equal to n, delta fn by delta xi x1, delta f1 by delta x2, delta fn by delta xn, then multiply by delta x1 delta x2 dash up to delta x1, and this will be equal to 0. You can see it from here. We can calculate these values and you will see we'll get back these equations again. This matrix can be shown in just one equation or in one matrix like this. This will be fi x1 dot x2 dot x2 naught dash up to xn naught plus delta fi by delta x1 delta fi by delta x2 plus dash up to delta fi by delta xn. X calculated all these matrices, calculate x is equal to x1 into delta xi naught, where I is equal to 1 2 dash up to n. When we vary this 1 2 and then this has to change to be f1 f2 f3 f4 up to fn. It will be delta f1 by delta x1 delta f2 by delta x1 delta f3 by delta x1 dash up to delta fn by delta x1. Similarly for this delta f1 by delta x2 delta f1 by delta x3 delta fn by delta x3. Similarly for this delta fn by delta delta f1 by delta x1 delta f2 by delta x1 delta fn by delta x1. This matrix will be x1 delta x1 not delta x2 not delta x now up to delta xn. So this is like this. The order of this matrix is n cross 1. The order of this matrix is n cross n. Again, this is known as Jacobian matrix, and the order of this matrix is n cross 1. So we can write it as simpler form. F naught is equal to j naught plus delta x naught. So again, f naught has a order n cross 1, j naught is order n cross n, and delta x is order n cross 1. So from this equation, delta x can be calculated. It will be equal to minus j naught inverse into f naught. So x1 will be equal to x naught plus delta x naught, or in general, xr plus 1 will be equal to xr plus delta xr, which is equal to xr minus gr inverse fr. This is an important result. So here we tried to do it for this for n equation, n nonlinear equations with n variables. So let us try to do it for our load flow problem. Now it is slightly clear. It will be very easy to do it for our load flow problem. First, before going into that, we'll have some explanations. This Newton-Raphson method is usually done in polar form, and the Gauss-Seidel method that we have done, that is usually done in rectangular form. So here also, this is also done in the rectangular form, but in usual practice, it has some advantages using it in the polar form. So we are going to use it in the polar form over here. So writing this static load flow equations, we know that Pi is equal to Vi summation j is equal to 1 to n Vj Yij cos of delta I minus delta j minus theta ij. Similarly, this Qi will be seen, only difference will be the sign term. These are a static load flow equation, and here we'll consider a system having only PQ buses except slack bus. That means we have a system having n bus system, and the number one system is slack bus, and from bus number 2 to up to n will be having only PQ buses. So as we know, in load flow problem, the first stage was to calculate Pi, Qi, Vi and delta I. But here we first calculate the voltage magnitude and phase angle. It is a part of the stage 1, and then we will go for the other calculations. So when we do that, voltage magnitude and phase angle, you'll see that we'll first see how many variables are there. Now consider system having only PQ bus except the slack bus, so it's the same. Numbering will be bus number 1 will be slack bus, load bus will be 2 to n, assuming n bus system. Total number of load buses will be n minus 1. So total number of variables, that is the voltage magnitude and phase angle. So how many voltage angle and phase angle we have to calculate? We have to calculate voltage and phase angle for every PQ bus. Since the number of PQ buses are n minus 1, and at every bus we have two variables, so the total variables will be 2n minus 2, because variable is voltage magnitude and phase angle. So at every bus, voltage magnitude and phase angle are the two variables. Total number of equations will also be equal to 2n minus 2, because at every bus P and Q are given, so we can make the equations. So it means we have And at every bus pi and qi are given, that's specified. So we can use these equations to calculate voltage and this voltage and phase angle. So we'll get the equation. Again, pi is equal to this equation where I is equal to 2 to n for PQ buses. So I can write it as like this: pi minus, I will take this term to this side, pi minus vi summation j is equal to 1 to n vj yij cos of delta I minus delta j minus theta ij is equal to 0, because as we have done in earlier case, let us say we have equation x square plus y square is equal to 13. So we have to make it as f of xy is equal to 0. So that means we have to take this 13 to this side. But here, since this pi is specified, it is almost of this type of equation. That is, this is pi minus this. I can take this over here. I can take like 13 minus x square minus y square is equal to 0. This becomes f of x is equal to 0. So that's why I have taken it to this side. So since this value is usually specified, I have written pi specified and pi calculated. It's the calculated value. Then we give this equation the values of this voltages, phase angle, initial values of voltages, phase angle, and wij will get the calculated value of pi. So I will take this equation like this: pi minus pi calculated is equal to 0. So this pi specified minus pi calculated will be equal to 0. I can take it as like this: delta pi is equal to 0. Similarly, we can do the same thing for the qi. So delta qi will be also equal to 0. So these are the two equations which we have to use for the Newton-Raphson method. Here I will vary from 2 to n, because we will have at every bus we will have this equation to be followed. So pi will be equal to pi calculated. Actually, this pi calculated will be equal to this value, because you can see this pi, we have taken this to be the calculated value, and this pi will be this value. I have written it again. Is a vi summation j is equal to 1 to n vj yij cos of delta I minus delta j minus theta ij, and I have written as pi. I have actually done dropped this cl also. I have written at pi, but this pi, you can see it from here, it is a function of delta 2, delta 3 up to delta n, because you will see when we vary this j from 1 to n, you will get all the deltas from 2 to n, which are variable, because delta 1 is given constant to be equal to 0. Similarly, we'll get the variables v2 to vn when j is equal to this, running from 2 to n. So that's why I have shown it as to be the function of deltas and voltages. Similarly, qi calculated, then qi, I have here dropped also the value of cl calculated, is the function of deltas and voltages, and it is it is equal to this value. So this is how we have calculated this, converted into the function, which then after which we can use the Newton-Raphson method to get the different values of the variables. I'll stop here. I will continue in the next class. Thank you.